Okay, so welcome everybody to the virtual time series seminar. We're very happy today to have Vladas Pipiras from UNC and Marie Duker from Cornell. Vladas, the floor is yours.
Thank you, Majid, and thank you for the opportunity to speak. I mentioned to Majid that I need to finish by the hour, so I'll try to take maybe even less time if possible. We'll see how it goes, and then have a little bit of time for discussion. I think it was mentioned that I'm joined by my discussant, so Marie Duker, who's also a co-author on one of the papers that I'm going to be focusing on. And I assume you can see my cursor, right? Is that correct?
Yes.
Okay.
Yes.
Okay. So, what is this? What is this all about? So, as the title suggests, we are looking at models for count data or count time series data. And when I say counts, I mean the time series that take values in 0, 1, 2, 3, etc., or a subset thereof. So the number of values can also be finite. So I'll be speaking about count time series. More generally, we can also think of just having ordinal data, that's been coded as counts, so that also falls into this framework. I don't think I really need to give examples to the audience here. Whenever you hear, data on the number of something, or again, if you have sort of ordinal data, we effectively dealing with counts. And more specifically, I'm going to be focusing on constructions which are based on latent Gaussian time series, so later unobserved Gaussian time series. Before just getting into it, few points to keep in mind. One is that perhaps contrary to continuous valued time series, there is no really universally preferred methodology for count time series. And what you're going to see here is sort of this one class of models, I think, with many appealing features that I'm going to discuss in a moment. And I'll mention at least maybe one other big class of models as I go along that this may be competing with. The talk is based, or will touch upon these 3 papers. The first one is published, and I'll be focusing on the 3rd paper here. Second one and the 3rd one are not published. I'll be focusing on the 3rd paper where Marie Duker is a co-author. So I'm going to start by describing the model in the univariate case. Actually, this is the subject of the first paper, giving you a bit of a sense of what this model is about. And then turn to the multivariate setting, in fact, even pushing it to a high-dimensional setting. I think I'm going to try to focus on more theory and methodology, but if there is time, I think at the very end, I'm just going to take it a bit lighter and show a few pictures on the application front. So what is this count time series model that we're going to be focusing on? And I should say that you can see from the days, these kind of models is something I've been thinking for several years now and continue doing so. So it's been an ongoing work. Now, what is this time series model? So I'm going to start with a univariate case and then explain it there. And once you understand how it looks like, I think you'll easily follow what happens in the multivariate / high dimensional setting. So here's the way the model is defined. So just for simplicity, I'm focusing on stationary time series. And whenever I say time series, these are going to be models indexed or data indexed by discrete time. So again, we're looking at a model for counts. Okay, so again, the values from 0, 1, 2, etc., or subset thereof. And the model itself has a number of components. So there is a stationary Gaussian series. So that's this latent component, unobserved components, ZT. It's standardized, so it has to mean 0, variance 1, which is important here for the construction of the model. And the autocovariance function of which, since it's standardized, so it's also the same as autocorrelation function. And just a bit on the notation side, I'm generally going to be using either lowercase or uppercase gamma for the autocovariance function. And rho, in the multivariate case, I'm going to write capital R for the autocorrelation function. So this object is parameterized by, let's say, some vector parameter, but vector or just single parameter beta. So you can think of just in one dimension, let's say, having autoregressive process with parameter phi. Since it's standardized, there would be only one parameter here denoted by phi. So there is this stationary Gaussian process, one element of the model, and then there's also the CDF, so denoted capital F, which comes from a family of some count distributions, which is parameterized by another potentially vector parameter theta. So for example, you can think of having the CDF of a Bernoulli distribution. So we're talking about only two values, 0, 1, 1 with probability P, and 0 with probability 1 minus P. So there's only one parameter here, P, that would be the theta. And the other notation I'm going to be using is I'm going to write F to the -1 is going to stand for the generalized inverse of F. So there's this latent Gaussian process, there's the CDF, there's one other here, capital phi, typical notation for the CDF of a standard normal distribution. So as you can see, the way the model is defined is that when it's taking this latent Gaussian series ZT, okay, so these are continuous valid series, one is applying the CDF of a standard normal to Z of t. So Z of t was real value, phi of Z of t now takes values from 0 to 1, and then we're taking the inverse of CDF. Okay, so again, it's something which takes values from 0 to 1 and maps it back to the real line. And since F is the count distribution, it maps those values back to the counts. And this function here, this composition of F minus 1 with phi, I'm just going to call it G, capital G. Okay, defined here. That's one of the notations I'm going to be using. So that's the construction of the model, abbreviated LGCM, so latent Gaussian count model. Once you look at the model, there are a few things, immediately to realize about the model. One is that, if I'm starting with the stationary Gaussian series, ZT, I'm just taking, a deterministic function of Z of t. XT is still going to be stationary. Okay, that's one thing. Now, the other thing is that, as we just discussed, obviously, XT is going to be taking count values because that's the way the inverse of F is taken. But not only that, the marginal distribution of X of t is going to be exactly F. And, I don't know to what extent this is sort of obvious to people, but a simple argument is it's the usual construction of getting variables with a given distribution, where you're taking a standard normal variable Z, and that's why it's taken to be standard normal. You apply the CDF of standard normal, so in which case phi Z becomes uniform now on the interval 0 to 1 as the variable. And then if you have a uniform variable, by taking the inverse of the CDF, that's quite easy to see, you get a variable which now has the F for the distribution. Okay, so indeed the marginal distribution of this XT at every single time, it's F. So the marginal distribution is F, and obviously because I'm allowing Z of t to be dependent over time, temporal dependence from ZT is now being inherited by XT in some way. And I'll be a bit more specific on the connection between the dependencies of X and Z in a moment. And as the model, you know, the way it's written here, it has, I guess, two parameters kind of to keep track of. So there's this marginal parameter theta. So the marginal of the CDF parameter f. The marginal parameter n beta, which the parameter controlling temporal dependence through the autocovariance function of z. So let me just walk through an example so you get a bit of a better sense of how this model is constructed in special cases. And I'm going to follow up on this Bernoulli case. And then the picture I'm going to show you is going to be having an underlying Gaussian autoregressive series of order 1. So let's just look at the CDF of a Bernoulli distribution with probability p. Again, so Bernoulli distribution, it's a simple count distribution, just concentrated on values 0 and 1. So 1 with probability p, 0 with probability 1 minus p. And here's the corresponding CDF of the Bernoulli distribution. So again, there is no probability up to 0. So we get 0 for any x smaller than 0. At 0, 0 is possible value, and the probability of 0 is 1 minus p. So it jumps to 1 minus p, then it stays constant all the way up to 1. And at 1 is another possible value. It jumps by p all the way up to 1. So that's the simple CDF. And the inverse function, you kind of have to visualize it and kind of flip it, you know. So the inverse function, again, just gives you back the possible values, in this case 0 and 1. And you would get 0 if u is from 0 to 1 minus p, and you would get 1 if u is from 1 minus p to 1. I'm not really putting here whether it's strict or not strict inequalities, because eventually we're kind of using some Gaussian or some continuous values for the argument. So this is the inverse CDF. Okay, and then for this particular case, the model, again, defined through this gz of t, or f minus 1 phi z of t, if I just substitute it. So I'm substituting phi zt for the u here. So again, I would get 0 or 1, depending on phi of z of t is smaller than this value or bigger than this value. And since phi is, it's a nice function, I can take the inverse of that. So this is the same as the process x of t takes value 0 if z of t, so the underlying latent Gaussian process, is smaller than this value, then phi minus 1, 1 minus p, and 1 if the underlying Gaussian process is bigger than that value. So for example, if p is equal to 1/2, phi minus 1 of 1/2, it's exactly the median of a standard normal distribution. We would be looking at 0. So you can see, and this is the same type of an argument you can make in a general case for general count distribution, that what happens is that you're having this latent process z of t, and then the continuous values, depending on the thresholds, like the ones here, are being sort of bent into count values. Okay, that's the way this model is constructed. So just to make this point even clearer, there's a little graphical illustration here. What you see here on the left side is a time plot of a latent Gaussian series, which follows autoregressive model of order 1 with parameter 5, which is 0.7. Okay, this is this black line. Then there are two. So it's the same model. So, Bernoulli model, value 0 to 1. This is the underlying Gaussian series. And then what is being presented here, one is looking at this model for two different probabilities. So probability 0.2, that corresponds to the blue color, you can see it, and probability 0.7, which corresponds to the red color, or this reddish color. Okay. And what you see here are those two thresholds from the previous slide, these ones here, the phi minus 1, 1 minus p. Again, this one for the probability 0.2. So again, and this is probability 0.7. Again, the way the resulting in this case, 0, 1 count process is constructed that whenever the underlying latent process, let's say, is bigger than this threshold, one is coding the process as 1. Whenever it's below this threshold, one is coding it as 0. And this is what's being presented on the right plot in blue here. Okay, so you had a bunch of values above here. That was 1. Okay, then one kind of went down below the threshold, this became 0, and so on and so forth. And then you can do the same type of plot for the threshold here corresponding to the probability 0.7, and you would get, again, a similar time plot of the resulting count series, but now on the be presented in the same plot in red color. Any questions the way the model is defined?
I have a remark. Can you hear me?
Yes.
Yes. If you have only 2 values, 0, 1, your model looks very much like a Markov switching model, right? With in a Markov switching model, you switch between 2 regimes, and there's some temporal dependence, some persistence, or something like that. It's very close.
Yeah, I think, I mean, I know just few things come to my mind. I usually sort of think a bit of, Markov switching process where, the dynamics sort of changes depending maybe in which regime you are, Here it's kind of the value which changes itself altogether. So in other words, you would get, for this threshold, you would get 1 here, and you would just get 0 here. That's sort of one observation. The other observation, which is not immediately, I think, obvious, is that, if you look at the latent autoregressive process of, or the one which is a Markov process, it's a simple Markov process. Actually, the resulting count process is not a Markov process. I think I'm saying that right. It's not immediately also, but it's not going to be a Markov process. I don't know if that answers your question, but these are sort of 2 immediate thoughts that come to my mind.
Okay, thank you.
Sure. Any other questions? So if there are no questions, let me just move on. This model has, I think, a number of interesting and appealing features that I'm gonna go over on the next slide, discussing them maybe without too much detail, before jumping into the multivariate settings. One is that I think similar constructions are used in things under different. I'm a bit hesitant to get into this thing, but I wouldn't be surprised if you've seen elements of this model in other settings, including the one where there is no really necessarily time dependence. That's one thing. And the other thing to keep in mind, that maybe why these models are popular, is that a Gaussian process or Gaussian distribution, and Gaussian distributions, Gaussian processes are generally nice to work with. That's number one. But 2, one thing which I like is that there are no real restrictions on the marginal distribution for the counts. And furthermore, that distribution, as we've just seen, is specified explicitly through this capital function CDF-F. So maybe just in contrast, one large competing class of models for count time series are these sort of GLM-like models. Just briefly, what happens in that case, one is not specifying the marginal distribution, but one is specifying a conditional distribution. For example, it would be xt, value of xt would be, let's say, specified as a conditional Poisson distribution, where Poisson parameter can depend on the past values. So it's not quite the marginal, it's a conditional marginal if you want. And then for those conditional marginals, it's not very clear what are the corresponding marginal distributions. It's an example. So this is a bit of a different model when it's specifying explicitly a marginal distribution, not a conditional marginal distribution. That's number 2. Now, number 3 is that this model turns out to have the most flexible or the largest possible correlation interval if you look at any 2 observations. Now, what do I mean by that? Let me just go back to the model, which is defined here. Now, what do I mean by that? It should be pretty obvious that through this construction, let's say I take a look at ZT at 2 different times, let's say T1 and T2. If those Z's at 2 different times are exactly the same, obviously the corresponding X is going to be exactly correlated. Obviously, they're going to be the same, so the correlation is going to be 1. And just means that on the positive side of the correlation, I'm reaching 1. I can go as high as I want. Now, if you ask this question, how negative the correlation can get between 2 different times, okay, it turns out that this model also allows for the largest negative correlation. The largest negative correlation turns out to correspond to the case where Z of t at one time is actually the exact opposite of Z of t on the other side, or at the other time. And this is a sort of a general known probability / statistics result, which I'm summarizing here. Namely, if you ask this question, where suppose you have 2 variables which follow some distribution f. Okay, so the marginals of x and y are f, and to asking now for which x and y with those marginal distribution, the correlation is going to be smallest. It does not necessarily have to be -1, but when is it that I'm going to get the smallest correlation? It turns out that you're going to get the smallest correlation if you take x and y to be these. So it's exactly what one has in the model, where one of these z's is z and the other one z is the z with the opposite sign. Okay, and again, the model that's considered allows it by taking z of t's of different size, if that's the case. That's number 3. Number 4, I'm focusing on the stationary model, but non-stationarity sort of can be incorporated if one wants through adding covariance to model parameters. That's one possibility. And the other one, which is not quite the case for other constructions, a bit like what you do with continuous data, you can also, if count data does not look stationary, you can also difference. Okay, and then fit this type of model. The only difference is that if you're working on the counts data into difference, potentially can get negative integer values. So this count model that I presented shouldn't be defined on counts, but it should be defined on the whole integer set. That's number 4. Number 5, and I'm going to be coming back to number 5 once I get to multidimensional setting. There's actually a relatively easy connection between autocovariance, autocorrelation functions between x and z. The one that you see written here in red. So it turns out that there is if you look at the relationship between the autocovariance functions, so of x and z, and this is at any lag h, it turns out there is a monotonically increasing function L, which depends only on the marginal distribution. Okay, so that relates autocovariance function of z at any lag to autocovariance function of x, again, at the same lag, again, any lag h. So there's, at the level of the second order properties, there's this nice decoupling that happens between the correlation structure in the autocovariance functions and the marginal distribution. Again, the L only depends on the marginal distribution. And if you rescale small l, we refer to it as a link function, so you remember. If you rescale the small l and you look at, there's a corresponding relationship between the autocorrelation functions. It's a bit nicer to look at because, again, this is the function which takes the value from -1 to 1, again, into -1 to 1. This is where the correlations live. So that seems to be nice, and actually in a moment we're going to be taking advantage of that. In fact, there is a simple way immediately to take advantage of these type relationships to estimate model parameters. So a simple way to do it, if you had to estimate model parameters, so theta is a marginal parameter. You know, I can just estimate theta in whichever way you want once you have count data. Okay, you can estimate it marginally. Now, on the other hand, for the beta, which drives the dependence of the latent process, suppose you're in a situation where I can estimate beta through the second order properties, so the autocovariance function of the latent process Z. So for example, you can do it for autoregressive processes. If that is the case, you know, I can't quite estimate gamma Z of H, from which I would get beta, because I'm not really observing Z, but I'm observing X. I can estimate autocovariance function of X, and then sort of take the inverse function of this link to estimate the corresponding autocovariance function of Z and get my estimate of the parameter beta. That's a simple way to do it, and this is exactly what I'm going to be doing in higher dimensions in a moment. In fact, this is a bit harder, but one can do maximum likelihood estimation for this model as well through likelihood approximation using sequential Monte Carlo of important sampling techniques. Now, this is a big topic on its own. I don't know how many people are familiar with this, but I'm not going to really be, you know, touching on this issue in this talk. So these are some what I think appealing and interesting features of this model in the univariate case, and again, more details you can find in one of the papers that I referenced in the very beginning. There are a number of other interesting things going on, especially, for example, computational issues around this sequential Monte Carlo sampling techniques. Now, on the negative side, you know, one aspect of these models that I think we struggled a bit, and I think follow-up work that I'm going to be discussing, trying to address, is that there hasn't been quite, I think, enough machinery, methodological / theoretical machinery built to work with these models. Just to give an example, for example, for these competing GLM-like count time series models, one actually has been able to push theory to fit these models or to work with these models in the high dimensional setting. So for example, one question has always been on our mind: can we do anything with these models in the high dimensional setting? And then, as I'm going to say in a moment, the answer is yes, and that's what I'm going to give you a little bit of an idea of. So in fact, I think we've been developing some of that theory that you know, becomes available to work with these models. So effectively, what we're saying is that it may not be the best strategy. I think the way these models are being developed, because there are, I think, lots of simpler questions one may have to deal with, maybe even before getting to the higher dimensional setting. But I think the message that I'm sending is that, look, you know, with this model, we can actually push this frontier. We can push this model and tools for this model all the way to the frontier. I think the current frontier of where sort of time series analysis is. And that's what I'm going to be sort of discussing over the next number of slides. So I'm going to turn now from this one-dimensional univariate case to the multivariate case and potentially high-dimensional case.
Can I just ask a question before you move on?
Absolutely, absolutely.
Do you have results on the identifiability of theta and beta from the moments, or from the likelihood function, for example?
Let's see, it's not something we necessarily address. I think one reason that it's not something we necessarily thought much is that, you know, as I said, theta is a marginal parameter. It's the distribution, it's the parameter for the marginal distribution, you know. So whenever I think there's identifiability on the marginal distribution, I think we should be okay there. You know, you think of like a Bernoulli distribution or something on 0 to 1. Are you okay with that point?
Sure, yeah.
Okay, now for the beta parameter, there may be something a bit more delicate here, you know, but if you truly believe in the model, you know, it just seems like, you know, this should be okay or something. I want to say it should be okay. There obviously, you know, like if you take an autoregressive model, there are obviously restrictions on the model for the identifiability purposes in terms of the parameter values or something. But beyond that, my inclination is to say that there are no really any additional constraints. But I may be wrong. Maybe I have to think a bit harder about this one. But that's my immediate reaction.
And is it possible to write down the likelihood function in closed form in this case, or not?
Yeah, I was a bit hesitant to get into the second point because it kind of opens the can of worms. The immediate answer is yes. And maybe just spending 1 minute, you shouldn't be surprised that it's possible. It immediately tells you what some of the difficulties are, because you can obviously write the likelihood in the Gaussian case of the underlying latent process, right? You can do it, and we know how to do it in the time series context. What happens with the likelihood for this model is that it's effectively the same likelihood in the continuous case, except that you have to integrate it now over the bins, okay, corresponding to the count values that you observe. Okay, so the likelihood is the same likelihood for the continuous process, integrated over those bins where the Gaussian process has to fall, so you get the observed value. And what this likelihood approximations do, again, they approximate these likelihoods again using sampling in a very intelligent way, sort of important sampling in a very intelligent. They surprisingly work very well, you know. But again, I'm kind of staying away. This is not the subject of this talk.
No, thanks.
All right. Anything else? Any other clarification question?
Can I ask you something related to this? Related to my sheet question?
Sure. Yeah.
Have you thought of specifying the model using the probability integral transform according to the conditional distribution of the latent variable, such that you would have the condition, I mean, the distribution of the count variable would be specified in that case. So if you go back one slide, instead of taking phi of x, phi of zt, you would take, like, suppose zt is AR1, phi of zt minus rho zt minus 1. And scaled by some the conditional variance, which would be 1 minus beta square, something like that. So in this case,
if I'm hearing, sorry, if I'm hearing it correctly, if I'm interpreting the question correctly, I think we looked at these type of constructions at some point, but this is already fairly flexible in our point. So for example, you can potentially ask, would it make sense to add z of t and maybe even zt minus 1 here or something? Is that a little bit what you're asking?
No, I'm saying to specify exactly there the probability integral transform given the distribution of zt given the past of zt. So in this case, that variable there, given the path of zt, would be uniform, and so xt given path of zt would be the one implied by f minus 1, like Poisson or binomial. So in that case, you would have control on this conditional distribution that you don't know now.
I think in this situation, I would take let's just take it offline, but I don't know what offline means in this setting. But maybe you can ask the discussant a bit at the end or something. That's
sure,
okay.
Of course. Yeah.
Okay, I don't have too much time, but I think the point with this is not really to run through the slides. So, thank you for the questions. I think it's important that, you guys, follow what's going on here. So I'm gonna jump now into this multivariate version of the model and kind of give you a little bit of idea, I think, of what is it that we've done. So in the multivariate setting, so we're focusing not on one series, but on D series, small d. So that's the dimension. X1t through xdt, each of them, again, count series. The construction of the model for each of these component series is exactly the one that you've just seen. So like x1t is defined as g1 of some underlying latent Gaussian series, where g of 1 has exactly the same construction as we've just discussed earlier. The only two additional elements are that one is that the marginal distribution for each dimension I can depend on the dimension. So you can see there's an f which depends on I. So in the first dimension I can get if I want Bernoulli counts. In the second dimension I can get Poisson counts, and so on and so forth. That's one important difference to keep in mind. And the other one is that not only I'm dealing with the univariate series for each of these Gaussian latent series, Z1t or ZDT, but if I combined all of them into vector series Z of t here, I'm still assuming that it's now a stationary d-vector Gaussian time series, where potentially not only I have dependence over time, but I'm also potentially having cross-dependence across the different dimensions. Otherwise, it's sort of the same type of a model. And to make things a little bit more concrete, also, because that's what I'm going to be presenting results in a moment, is that suppose furthermore that the underlying Gaussian process Z of t, Gaussian series Z of t, let's say follows a stationary vector or regressive model of order p, the one that you hear written here. And the question I'm asking here is, how would I be estimating this vector or regressive coefficient matrices, so d by d matrices, psi1 all the way to psi p. Okay, and if I vectorize them, this is my parameter beta. Okay, so I have marginal parameters here, theta i's, because they potentially depend on I, but also have this parameter vector beta here, which drives my dependence, temporal and cross dependence across the dimensions. And not only that, I'm going to make it even harder here. I'm saying, how can one do it in the high dimensional setting? So I'm thinking about large D, potentially even larger than the sample size. Maybe I should say here, the number of time points that I have capital T. That's the setting that I'm pushing this towards. It's not something we got, but an example of this kind of situation, that you can keep in mind is suppose you have a large dynamic 0-1 network. So you have a large network, nodes are connected, that evolves over time, and dimension just corresponds to an edge between two nodes, whether you have it or not. If you have it, you code it as 1. If you do not have it, you code it as 0, as an example. So even for a small number of nodes, the number of edges potentially is large. So again, one is looking at the situation of large D, large dimension, and small sample size, a small number of time points, capital T. How would one estimate these transition matrices? Psi1 to psi p. And that's what I'm going to spend the next slides explaining. So let me write this, this is just a regression model. So I'm going to write this in a linear form for observation Z1 through ZT. And that's what you see here at the top of this slide. So I'm gathering the observations on the left. I'm starting with p plus 1 because I'm regressing on the right-hand side on p to 1. And then finishing with Z of t. So there's going to be a bit of a change in notation because I'm really only having not quite capital T times, but here on the left side, I really have T minus P time points. I'm going to call this capital N. The number of parameters, unknown parameters here, each of these are d by d matrices. So each of them have d squared number of parameters, and there are p of those. So just focusing on how many unknown parameters are here is actually p d squared, which I'm calling q. And then this matrix here of these unknown parameters, if I vectorize it, I'm calling it beta 0 or beta hat if I'm estimating that. So this seems like, you know, a linear model, relatively simple. If I had to estimate it in a lower dimension, I can just use run linear regression. And if I use linear regression, I can also write the solution actually as I'm minimizing the sum of these two terms over beta, where small and big gamma are the ones that should be defined here. So that's the usual regression setting. If I wanted to, if I'm working in a high dimensional setting, so I can't really run least squares, typically people do sparse estimation by adding this sparse penalty. So L1 penalty, so just the sum of absolute value of the coefficients multiplied with the penalty parameter. So the larger the penalty parameter, the sparser the solution is. So if I actually observe disease, okay, this is the way one estimates the unknown parameters beta, okay, in the sparse regime. Actually, this case was considered in the seminal paper by Basu and Michaelidis, who developed a theory for showing consistency and some other things of the resulting estimate. Now, in our situation, these are not observed, okay? And to get around this issue, we do a bit what I was describing to you as a simple way of estimating things. So what do I know? I know that if I look at these quantities, gamma hat, big and small, or whatever defines them, so this gamma z small and gamma z big, okay, which are sort of this average. These are just sample covariances, because if you look at what those things are, there are some z's, some components of the z's at some times, and I'm essentially taking the products and averaging them. These are just sample covariances of some z's. These are also sample covariances of z's. So again, these are sample quantities for the second order properties of z's. Actually, the corresponding, I can look at the corresponding population quantities if you took the expected value. I'm just denoting them in the same way without the hats. These are second order properties of z's. I know that I have a relationship through those link functions that allow me to get to gamma z's with exactly the same corresponding quantities for x's, the observed data. So again, all I would do, I would just estimate these through x's, apply those inverses of the link functions to estimate these quantities. And this would be my estimate. I think I'm a bit running out of time. I didn't really want to rush through anyway, but what I have over the next slide is explaining a little bit what that link function comes from, but I'm not going to spend a lot of time here. I'm just going to show you the way the exact relationship looks like. Again, it's the type of the relationship that allows you to relate. This is written because we're dealing with multivariate time series. This is the ith j component of autocovariance function of x at like h. Again, the point being that one can relate this to the corresponding value for the latent process, z ij, again, through some function, deterministic function, which only depends on the marginal parameters in dimension I and j. There's a way to compute it, and there's a bit of an explanation why it comes in, and it can be computed if one needs to in practice. Again, the point being is that there is this link function L, which relates, this is written in the shorthand notation, which relates the autocorrelation function of z, that's the same as autocovariance function of z at like h, this is written component wise, to that of the corresponding value of x. And the same thing happens with the correlation functions. Something I may come back to keep in mind, there are actually explicit forms for derivatives of these link functions that one can work with. In particular, one knows that derivatives are positive. So these are monotonically increasing functions. One knows that inverses exist. So I can actually, again, if I wanted, I could express the autocovariance function of Z in terms of the inverse of those links on X. And this is what I was referring to. I can always get to autocovariance or second order properties of X by looking at those for X and applying the inverse link function. So I have the L, I have the L minus 1, the inverse. From the data, I don't really know the marginal parameters, but I can estimate those from data. So I can be talking about L hats or L hats inverses. I have on the next slide, I have just the way these link functions, this is the standardized one that takes -1 to 1 to -1 to 1. So this is, think of it as a correlation of Z. This is the correlations for X. For example, the black line corresponds to the case. This is all Bernoulli case. So corresponds to, in one dimension, one has Bernoulli counts with parameter 0.4. In the other one, one also has Bernoulli counts with parameter 0.4. And some of the other colors take those parameters to be different. Again, the way you see those link functions are monotonically increasing. When the two parameters are the same, you know, this is sort of univariate case. At 1, they should be going all the way up to 1. But on the negative side, they typically do not go all the way to -1. And again, one other interesting thing to keep in mind that typically these curves are below the 45-degree angle, which means that if I have certain correlation on the Z scale for the underlying latent process, if I look at the corresponding correlation for X, it's typically going to be smaller. So the model suppresses correlations of the latent variables if you look at the correlations for the X. Getting back to the sparse estimation, it's a similar slide to what I had before. I'm just adding what I said through these equations in red here. Again, if Z's are unobserved, I can still pretty much do the same thing from the estimation standpoint. Okay, the only difference being I do not observe disease, but I can get to second order properties by looking at those for X observed data. So I'm going to be using data to estimate some sort of sample covariances for X. These are the quantities. I'm going to be estimating the link functions, taking the inverses, and that should give me the estimates of the corresponding second order properties of the latent Gaussian process Z. And these are the ones I'm going to be using in this sparse estimation for the parameters of the latent process. Okay, so this is what we do, practically speaking, and surprisingly or not, we see in practice that things work pretty well. You know, if you try it on the similar data as an example. So what we did is actually in this paper that I wanted to talk to, but I see that I'm running out of time, is develop theory for showing consistency of estimation if this is the way you do estimation in the high dimensional sparse regime. And I think if there are no objections, since I do not have time and I do not really want to rush, I'm actually going to skip the theory altogether. Okay. Let me just say two things. I do not know how many people are familiar with Basu and Michaelidis' paper. I think difficulty with presenting theory, and had I had more time, I would have tried to do it over 4 slides. It's not an easy job, I think, because I think for those who haven't seen this paper, I think it's going to be kind of a bit of a challenge. If anything, it may motivate you to look at some of these techniques in the higher dimensional setting. Now, for those who are kind of super familiar with the way things done, when you observe disease, I think would probably appreciate the kind of results that we've gotten. So I don't know, for better or worse, I'm going to skip the theory and I'm just going to take a few minutes to conclude with some pictures. Now the pictures don't quite, so it's a pictures with some pictures from the applications that we did applying these type of models. It's not exactly this model, so it's not exactly this model that I'm going to be showing the things for. So when I say this model, I'm not going to be assuming that the underlying Gaussian series evolves as a vector or regressive process, for which we have this theory that I'm not going to be talking about. I'm going to show you a few pictures when it's exactly the same model, but the Z's evolve as a dynamic factor model. So I'm going to skip those slides. The ones who are very upsetting me as well, just close your eyes for a few seconds. So I'm going to skip this theory stuff. And I'm going to be talking, just show you a few pictures on the lighter side. So you at least to come out with sort of just general feel of, you know, what the data might be looking at, what these models may be serving, and so on and so forth. So this is taken from this third paper that I mentioned at the very beginning. So it's the same type of model, but what the underlying Gaussian series, okay, so again, d-dimensional, is driven not by the vector regressive dynamics, by a dynamic factor model of this form in its static form. So as usual, you have a loading matrix, lambda. So this is D by R matrix, where R is of a smaller dimension. So and factor series, so factor series, which again is of a smaller dimension, and some error added. Again, everything is Gaussian here because the resulting process has to be Gaussian. So for example, think of the underlying factor series of a lower dimension now evolving as a vector regressive process of order 1. So in that paper, sort of the application that we looked at, or the data for that application is the one that you see being presented here. What happens here that there were a few individuals, but this is presented for one individual. So for that particular individual, daily, one tracks the way that individual associates with 30 emotions. So there are actually 30 series in these plots. Those 30 emotions are also divided into 5 categories. You can think of this sort of as factors if you want. 5 categories, they call them big 5. If anything, what we do here is a little bit like confirmatory factor analysis for the count data. And the way the count data arises here, it's more like an ordinal data where you know, on each of these emotions, a person has to say how well they associate with it on that given day. And the scale goes, let's say, in here from 1, 2, 3, 4, 5. Okay, so one goes from 1 to 5. I think the one reason that we're looking at the factor model, because you know, I think some of these plots suggest that even across these categories, individual series sort of seem to be moving together, again suggesting potentially an underlying factor model. I think this factor model is also suggested if you look at this is just the correlation matrix. It's 30 by 30 of the observed count data. Again, kind of looks blocky. This is ordered according to those categories, so it looks blocky, at least part of it, suggesting a factor structure. This is this autocorrelation function, but at lag 1 of the count data. It's a bit less maybe obvious what it is. Getting back to the model, this model has similar features as vector regressive model in that you can actually estimate the loading matrix. As you know, the simplest way is just do like principal component analysis. Principal component analysis involves covariance or correlation matrix of Z, so second order properties of Z. And similarly, we can kind of push that envelope to estimate psi also through the second order properties. Again, I'm not really observing the Z, but I'm observing the X. And I know that through those sling functions, I can get to the second order properties of Z by looking at the corresponding second order properties of X. So I can, in principle, in the same way, I should be able to estimate the loading matrix. I should be able to estimate this transition matrix. And this is what kind of just presenting you on this slide. This is the estimated loading matrix of the latent process. This is the estimated transition matrix. Because of this factor structure, it kind of also, you see there's a bit of a blocky structure. Some of the values in the transition matrix are pretty large, suggesting that there is temporal dependence in the data. And one of my psychometrics colleagues kind of would be able to interpret some of these values for the corresponding factors. We were looking at these models to assess the forecasting performance. I'm not getting actually in how does one do forecasting with these models, but these are sort of the typical pictures where we look where the bottom row is forecasting results out of sample compared to some baselines. And I'm going to just finish with the conclusion slide. So what I did today is, I think, introducing to those who haven't seen it, this latent Gaussian count model. Hopefully you see that it has a number of interesting, appealing, and interesting features. The thing which I tried to emphasize, but I didn't quite get through to the high dimension, one can actually work with this model, including high dimensions. And just giving a little bit of a flavor, the kind of applications that these models can be used. Indeed, they can be readily used in applications. And there are a few future works that we're thinking about. I think I'm going to stop here and thank you for your attention.
Thank you, Vladas, for the wonderful presentation. So I'm going to stop the recording.